All right, so today we're going to dive in and we're going to start solving one-dimensional physics problems. Um, this is probably what you had in mind about what you were going to be doing when you signed up for a physics class, is solving this kind of problem. Okay, so we're going to dive in and we're going to see that these one-dimensional motion problems are not too bad. But you got to practice this skill a whole bunch, and then we move on to doing two-dimensional motion problems and force problems. Then you can really just build on this foundation that we're going to learn today. So here's a set of 5 equations, and these 5 equations describe motion in one dimension with constant acceleration. Okay, so these are one-dimensional motion for constant acceleration. Who came up with these? Well, Isaac Newton. We're going to talk more about how he came up with them when we get to chapter 5. But these are the basic equations that we're going to use to solve some physics problems. So let's just jump right in. These 5 equations, 1 and 2 are the basics. You'll see those in every single physics textbook. Okay, these 2 are the basics. Now, you'll notice that equation number 3 does not have t in there. Now, I'm not going to necessarily ask you to do this, but were you to solve this equation for t and plug it in down here, you could arrive at equation number 3. And indeed, that's what it says. 1 and 2 are the basics. 3, 4, and 5 can be obtained algebraically from 1 and 2. 1, 2, and 3 are given in your book. Okay, so every physics book everywhere gives you these first 2. Most introductory treatments give you the first 3. I give 5 equations. And the reason I give 5 equations is this is a trick I learned from when I worked for the Princeton Review, which is a test prep company. And I give these 5 equations for this reason. Notice that in each of these there are 5 variables. We have delta x, v final, v initial, delta t, and acceleration. Those are our 5 variables that occur in these equations. And I've arranged them the way that I have, because if you'll notice, in each one of these, there is one of these 5 that is missing. And so in equation number 1, notice we don't have delta x. In equation 2, we don't have v final. In equation 3, we don't have delta t. Equation 4 has no acceleration. And equation 5 has no v initial. So it's a very tidy way of arranging these things. And our general strategy is that we find the equation that has 3 things we know and 1 thing we don't know. And that's the equation that we use to solve our problem. That's our general strategy. If we wanted to be just a little bit more specific about our strategy, we could look at this slide, and this is from your textbook. So our general problem-solving strategy has 3 parts. Prepare. We're going to set up the problem first. And so in this step, what we do is we draw our picture, and we collect our necessary information. We make our list of 5 variables, and we start filling in the missing pieces. We see what we have and what we're asked for, and that will help guide us to the proper equation to use. And then we solve. We do the necessary mathematics. Typically, that's a little bit of algebra, maybe a little bit of trig. And then this last step is really important. It's a hard one for me to grade, but it's no less important than any of these other steps. And that is, just check to make sure that your answer makes sense, right? Sometimes we might spend 5, 10, 15 longer minutes working on these problems. And it's good, you always at the end, you just got to circle back around to the beginning of the problem and say, did I answer the thing that I was asked to answer? And does my answer make sense? If I'm asked, how fast was the car traveling? And I get 10 times 10 to the 14th meters per second, then that's definitely wrong, right? So you need to look at this and say, okay, well, does my answer make sense? If I'm asked for the speed of a car, is it a reasonable speed for a car? Okay, let's just try one. Here we go. The first thing we're going to do, this is a physics problem, the first thing you want to do is just read the whole thing. And don't let yourself get hung up on the numbers, or don't try and understand every single word right away. You just want to read it and let it wash over you, and then we're going to go back and we're going to read it more carefully and slow down a little bit. So, a cyclist is stopped at a red light. When the light turns green, he begins accelerating at 1.2 meters per second. How many seconds after the light turns green does he reach his cruising speed of 6 meters per second? Okay, so I just read it quickly. I sort of let it wash over me, and I have a visualization of the problem in my mind, but I didn't get too worked up about any details. Now I'm going to go back, I'm going to read the problem more slowly, and I'm going to start to transfer some of these ideas onto my piece of paper. So I'm going to go back. A cyclist is stopped at a red light. Okay, so apparently this problem is about a cyclist. I'm not sure, I'm just going to draw myself a quick picture here. There's my cyclist, and he's stopped at a red light. It says, when the light turns green, he begins accelerating at 1.2 meters per second. So he's going to head over this direction. How many seconds does it take him to reach his cruising speed of 6 meters per second? So he's going to be over here, and his V final is 6 meters per second. Okay, so he starts here, he goes over here. Okay, now I can really visualize this problem now. Let's fill in our list here. See what we have and what we don't have. Delta x. That's the distance, right? That's a change in position. Did they tell us how far he went? No, they didn't. So we're just going to put a... So we don't know how far he went. So we'll just put a question mark there. V final. Do we know that? Yes, we do. That's 6 meters per second. V initial. Ooh, this is a tricky one to look out for. They didn't explicitly tell us what his initial velocity was, but they say it is stopped at a red light. Well, stopped at a red light, that means his initial velocity is 0 meters per second. Moving on, how many seconds, or excuse me, next is delta t. Do we know delta t? No, in fact, that's what we're asked for. It says how many seconds after the light turns green. So we're looking for delta t. Acceleration, did they give us that? Yes, they did. 1.2 meters per second squared. Okay, so we look at this and we say, okay, we know 3 out of the 5. Part of why I like arranging these equations as I do into the big 5 is that with the big 5 arranged as it is, anytime you have 3 out of the 5 of this list filled in, you can always find the other 2. As long as you have 3 out of the 5, you can always find the other 2. So one hint here, and this is not necessarily like the go-to thing, but it's a good hint, is there anything here that I'm neither asked for nor given? And there is, right? Delta x, I'm neither asked for nor given delta x. So let's go back and let's look at our big 5. So get your sheet out, your big 5, and try and find the equation that does not have delta x in it. Again, it's just kind of a hint. The real definitely works every single time strategy is find the equation that has 3 things you know and 1 thing you don't know. A good clue is delta x, I'm not asked for it nor given it. Which equation does not have delta x? So now I'm going to look at this and oh, I can see that pretty quickly. Equation number 1 does not have delta x in it. So that's a good hint that we might start with equation number 1. I'm going to write it down. And since we're in 1 dimension, I can drop the x. There's no ambiguity here. We only have motion in 1 direction. Now, what I suggest is next you plug in anything that's a 0 right away. And indeed, we do have 0 right here. And now I can do my algebra and isolate delta t. So we have delta t is equal to v final divided by a. Notice I have v final and I have a, so at this point I can just plug in. Delta t equals v final, 6 meters per second, divided by 1.2 meters per second squared. And that equals 5 seconds. Five seconds. 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000. Is that a reasonable amount of time for a cyclist to get up to speed? I think so. Did I answer the question? How many seconds? Yes, I did. So I answered the question, and it's a reasonable number. So I've done my assess step. I think we're good. Let's just try another one. Okay, again, we're going to read it quickly. Just let it flow over us. And then we're going to come back and we're going to read it more carefully and start transferring information to our paper, and then we'll solve it. So First time, we're just trying to get a feeling for what the problem's about. As you drive your car at 15 meters per second, you see a child's ball roll into the street ahead of you. You hit the brakes and stop as quickly as you can. In this case, you come to rest in 1.5 seconds. How far does your car travel as you brake to a stop? Okay. I can visualize it, something about a car and a ball. Now I'm going to go back and I'm going to read it a little bit more slowly. I'm going to start transferring information to my paper and including a drawing. So as you drive your car at 15 meters per second, you see a child's ball roll into the street ahead of you. Okay, I can handle that statement. Here's my car. And it tells me I'm driving 15 meters per second. And we see a ball in the street ahead of you. Okay, I don't know. I guess we could draw a ball here. Ah! Okay. Maybe the ball's a little farther out here. I don't know. Okay. And it says, you hit the brakes and stop as quickly as you can. In this case, you come to rest in 1.5 seconds. How far does your car travel as you brake to a stop? Okay, so it says how far does it travel. So that would be something like this, right? Delta X, I guess. And it tells us it comes to rest in 1.5 seconds. Okay, well, let's make our list of 5 variables. Again, delta X, delta T, V initial, V final, and A. All right, delta X, don't know. Delta T, ooh, they did tell us that. That's 1.5 seconds. V initial, 15 meters per second, right? V final, again, they didn't say 0 meters per second, but they did say comes to a stop, so that must be 0. And the acceleration, ooh, didn't tell us, did they? Okay, now, is there anything in here that we were neither asked for nor given? Acceleration, right? So I was neither asked for nor given acceleration. Okay, so if I look at this, which equation does not have acceleration in it? That's our clue. Equation number 4 has no acceleration in it. And notice that it has 3 things we know and 1 thing we don't know. And we don't even have to do any algebra here because it's already solved for delta x. So delta x equals 1/2 times v initial plus v final times delta t. Again, let's plug in zeros right away. V final is 0, so we'll just cancel that right out. And so then we have delta x equals 1/2 times v initial, 15 meters per second, times delta t, 1.5 seconds. And so now I run my calculator and I get 11.25 meters.
Come on.
And, to 2 sig figs, we might want to report that as 11. Okay. Is that a reasonable number? Multiply it by about 3, so 33 feet. A little bit more than 33 feet. That's a pretty reasonable number. Did we ask what was did we answer the question that was asked? It says, how far does your car travel? Yeah, I think we did. Yeah. Okay.